Okay, hello and welcome back, everybody. So a bit of a shorter video again. We're just going to get halfway through section 5.3, so we're going to get through this section that I've labeled as defining Green's functions. Green's functions is clearly the title of the section, so we're going to try to learn as much as we can about these, for right now, mysterious objects, but they won't be too mysterious for too long. When you took Calculus 3 or multivariable calculus, you probably had to cover some other theorems that were named after Green. He's got like Green's theorem or identity. He technically has like three identities. They're all kind of the same thing. And then the theorem is closely related to that. So same Green. He was born in the 1800s, lived in the 1800s, made a lot of work in electrodynamics. So kind of right around the same work as Maxwell, but kind of preceding Maxwell in terms of the electrodynamics. Anyway, he's got a nice way of thinking about solving differential equations. In reality, he kind of only championed this for Laplace's equation to describe the density of the electromagnetic potential. You can do that with Laplace's equation, so that was really what Green did. But his notion has been extended to all sorts of PDEs, really linear PDEs. You got to stick with linear to make this work. But what we want to think about when we're thinking about Green's functions is this object. And this is just the second order PDE version of this object. We encountered this back in chapter 4. And really, we encountered it in the sense of the Fourier methods, where basically we were trying to understand this inverse, this 1 divided by some collection of derivatives and functions. You can't, of course, consider it as a 1 divided by, because derivatives don't have such a thing. You can't divide by a derivative, but you can think about the inverse of a derivative as an antiderivative. Unfortunately, because 1 over a plus b is not equal to 1 over a plus 1 over b, hopefully none of you have forgotten that. Because of that, you don't have this nice property that you can just like pass the inverse sign to each of these terms. That's a big no-no to try to invert all of those individually. So you can't do that. So something much more complicated needs to happen if you try to invert a derivative operator. And we like to pretend like derivative operators are numbers. This was the Fourier method. Wherein we truly, if I can spell, truly could take 1 divided by some collection of numbers to invert it, or a function, right? The Fourier multiplier was really a function, but it's a number for each input. Green's function is really trying to do the same thing, except we're going to be doing the same thing in the context of matrices. We're going to, Green's function are interpretations of this inverse symbol in the sense of matrix inversion. So instead of numerical inversion, that's what we got away with the Fourier methods, we can think of matrix inversion. And that's really Green's functions methods. So what do I mean by matrix inversion? We have to jump way back here to the very first section of this chapter. This is why I spent 2 sections, one on the integral transforms and then the later section on the Dirac delta function. You'll see why I basically needed to cover both of them to get to Green's functions. But we're thinking of matrices in the sense of that the linear transforms or the integral transforms were matrices, right? The integral transforms we were working with earlier were the same thing as matrix multiplication on a vector. We had this wonderful proposition right here that says integral transforms describe infinite dimensional, quote, matrix multiplication. So this was kind of like a really cool theorem that we were able to come up with. And now that we understand that this can be a partial differential equation operator, we can construct its matrix inverse. And by matrix inverse, we should really mean integral transform inverse. And when we construct that matrix inverse or integral transform inverse as a function of 2 variables, right? Because a matrix is always a function of 1, 2 variables, and integral transform is a function, or the kernel is a function of 2 variables. Its matrix inverse or the kernel inverse will be a function of 2 variables. And that's going to be our Green's function. So that's really what I'm describing in the next few paragraphs of the Green's function section. I describe that, hey, we have matrix inverses, where no matter which side I multiply a matrix on against another matrix, I recover the identity. Well, let's just recall that the integral transform version of the identity is the delta function. And so what I want is a version of integral transforming one kernel against another. And of course, the matrix multiplication is basically like an integral transform, right? This operation is the quote-unquote integral transform. So the fact that you're doing that multiplication, that's this multiplication and this integral in both cases. And so I'm searching for a function k inverse for which, when I perform this version of matrix multiplication, this infinite dimensional version of matrix multiplication, which is represented by an integral transform, what I recover is the identity kernel. So I want to multiply two kernels together and recover the identity kernel. That's what it would mean to invert an integral kernel. And since I know I can represent differential operators as integral kernels, as I did in these last two examples of our last video, there's a differential operator that's a kernel. If I have a notion of inverting this under integral transform multiplication, whatever you consider that to be, kind of like matrix multiplication, if I have a notion of inverting that and recovering the delta function out of it, then I can solve my PDE. So this is really Green's functions for you. So we're going to call this function k inverse the Green's function. And I do want to be careful with everybody, even though I've kind of been covering this the whole time. The notation k inverse does not describe a reciprocal function. The inverse in this sense is its own operation, distinct from reciprocals. So don't just pretend like you're going to make your life easy and say that 1 over k yx is k inverse yx. Please do not do this. I don't want to see that. So don't do that. Keep that in mind. It's its own thing. K inverse is just whatever it is. Now we get to our definition for a Green's function. We're going to start with an nth order linear PDE. And let's just be careful about why this describes the nth order linear PDE. What have I been saying the whole time when I represent my PDEs like this? I'm saying AK is a K tensor field. And then I have this dot where that's a scalar product against the Kth exterior product or outer product of the gradient with itself. So jump all the way back to chapter 2 and you'll see how all of those are defined. This should look similar to how we were taking higher order or higher dimensional Taylor series. From chapter 2. So if you go all the way back to chapter 2, you'll find that with the higher dimensional Taylor series. Basically just think you can expand your gradient over and over again. The kth power is a K tensor. This is some sort of K tensor of all combinations of derivatives. And then this is another K tensor, which is a K tensor field that depends on X. So K tensor field dependent on X. And when you take the scalar product of the two of them, you just add all of those terms together. So you basically have whatever combination of functions you want dependent on the variable X against any combination of nth order derivatives. So that's why it's an nth order PDE. Linear because every operation here is a linear operation. So that's why that's kind of your generic nth order linear PDE. A lot of authors will represent this different ways. They'll talk about multi-indexes, which is another way of kind of getting at the same thing. This is the way I like to represent them. And what we know from the last section is that we can just translate this operator into a kernel, k. In fact, it's this kernel as well. So we can translate that operator into a kernel k. We define the Green's function as the kernel, or just the function of two variables is all it is, right? So the Green's function of boundary value 0, and that corresponds to the fact that our original PDE had boundary value 0, which itself corresponds to the fact that we were in the space of test functions. Recall the space of test functions as the natural space in which this Dirac delta function is defined. That was in the last video. We just say that it's the Green's function of boundary value 0 because we're sitting inside of this space where necessarily all of our functions have 0 boundary values. The Green's function is this inverse, k inverse, whatever that function of two variables. They may be higher dimensional variables, right? They may be vectors individually. Whatever that function is, when we compute this integral transform of one kernel against the other kernel, as long as I get the delta function out of it, that's a Green's function. Now that's extremely abstract and theoretic. So I think most of the time Green's functions is taught, most of the time that I was taught Green's function, most of the time that I'm looking for Green's functions. I do not use this definition. It's a bad definition to use if you're actually trying to find these or work with these or think about them conceptually. The next proposition is actually the definition that we're thinking about. The Green's function of boundary value 0 is just a function, and we're going to notate it by g sub omega now, because omega is describing the fact that this is our domain. G sub omega is a function of two variables, omega and its closure. Let's just recall really quick. This is defined by omega and its boundary combined. So that's called the closure of omega. So g is just a two-dimensional function on omega and its closure, satisfying that when you plug g as a two-dimensional function into the PDE, the original same PDE as before, and we take our derivatives in the x variable. So we don't really worry about this y variable, just kind of forget about it for now. So we're taking derivatives in the x variable, as long as that's this term here, as long as this function satisfies that when we compute our PDE operator against it, as long as we get the delta function out, that's the Green's function. And also, hey, the Green's function needs to satisfy the 0 boundary condition, and that's the boundary specifically in the x variable. Okay, so we're looking at the x variable here in boundary. Needs to be equal to 0. So that's what makes the Green function have boundary value 0. Really what you want to think about is just get rid of this variable y all the way. Just forget about it. It sits around as a parameter, but it's kind of the parameter that has to sit inside this delta function, in the right-hand side. So it has to be there, but really you're thinking about what is the PDE acting on a function giving me a Dirac delta function. And then, by the way, it needs to always be equal to 0 on the boundary. That's going to be the Green's function of boundary value 0. And it corresponds to the same thing. So you would find out that if a PDE satisfies this, then it also satisfies this. And it's all because of the Dirac delta function on the right-hand side, one way or the other. I do have a proof for that. Make sure that you realize that they're the same. But we actually try to extend this just a little bit, because I have this paragraph that says, by the way, a lot of PDEs don't necessarily have 0 on the boundary. This is an incredibly strong condition. It's a common condition, super common, super normal. I'll call it a normal condition, or common. But certainly not universal. Right, we definitely exist in a world where things are not 0 on the boundaries, and boundaries exist. So we maybe want to extend the notion of Green's functions away from the boundary value always being 0, even though we kind of had to rely on that to define them. We had to rely on that for the Dirac delta function to be well defined. What we can do now is define Green's boundary correctors. And I do have a little footnote on the previous page that says the name for these functions are believed to be unique to this book. So you'll always see things similar to the Green's boundary correctors in other books. They gain different names. Sometimes they're just embedded in the definition of the Green's function. Other times they just show up in a theorem without a specific name. I decided to give them the name the Green's boundary corrector because it corrects for the value of the Green's function on the boundary. The boundary was originally equal to 0. We're going to correct for that with this Green's boundary corrector. So what is the Green's boundary corrector? It kind of has a very similar definition to the Green's function itself, and there are j of them, or really there are n minus 1 of these. But the jth version of it, basically, you take the PDE and you act the PDE on the Green's function, but instead of getting the delta function out of it, now we get 0 on the PDE. But on the boundary, if we take the kth power of this is the outward unit normal on boundary. So if we take the kth outward unit normal on the boundary of the jth boundary corrector, I'm looking for the delta function specifically when j is k. So if these two numbers align, I want to get the delta function out of it. If those two numbers don't align, I want to get a 0. So what's actually going on here? This is just the opposite of the Green's function. So Green's function was delta in the PDE, 0 on the boundary. The corrector is 0 in the PDE, and it's delta on the boundary. So that's the only difference. And then, we're talking about having j copies of these, and we need j copies of them because potentially we could have a lot of boundary conditions to satisfy. So it's just a question of how many boundary conditions do I actually have to satisfy. That's as many correctors as I need. In the event that I'm a first order PDE, I have one boundary condition to satisfy, which is my 0th order boundary condition. Then I only need one Green's boundary corrector. if I'm a 42nd order PDE, I may need up to 41 boundary correctors. So it just kind of depends on the specific PDE, how many boundary correctors you need. And then this next theorem, even though we have a bit of a shorter section in the book today, this is perhaps the theoretically most important theorem of the book. It's maybe not the easiest in practice, but in theory, this is maybe the strongest theorem we have in the entire book. This is called the Green's representation theorem. What we have here is we're going to take some Green's functions of boundary value 0, and we're going to take their correctors, the jth correctors, Green's boundary correctors, as defined in the proposition and definition as you would want, to specifically these PDEs. We can find a solution to that PDE, which is the generic. This is the nth order linear PDE. There are no other nth order linear PDEs. This is it. You can find the solution right here. It's given by this function. Now, the downside is that we actually don't know what these look like in a lot of situations. So don't imagine that this is like immediately solves every PDE the entire world has given you. You don't know what G and you know, G on the boundary and G on the domain look like in a lot of cases. But, you know, suppose somebody from on high has given them to you, then you have them and you can solve the linear PDE. So it's solved by the following at the bottom. So let's see what's actually going on here. What's going on is we initially have this computation, which this is an integral transform over omega. And here we have an integral transform over the boundary of omega. So we've got one integral transform over omega, and we have potentially a sum from 0 to n minus 1, that's j, that's that j. This is why we potentially need j different Green's boundary correctors of integral transforms over the boundary. So we just take this sum of the integral transform over the domain itself, and then integral transforms over the boundary, and we've solved our PDE. Now keep in mind what's going on here. We've got the f right there, that's going in here, and we have gk that's going in right there. And in fact, this should be, that's a typo, this should be gj. gj is going in right there. So we just have a nice sum of a lot of integral transforms. This is why integral transforms are so important. Defining Green's functions is why the Dirac delta function is so important. And you know, supposing we can actually find these lovely objects, which is not the easiest thing in the world, but supposing we can find them, we can solve whatever linear PDE we want. So that's really where the power is in these Green's functions. And I have a nice little proof there that verifies it actually exists for you. And then in the next section, we're going to run into actually utilizing these. So we're going to stop there for today. But I really want us to sit down and look at this theorem, the Green's representation theorem, and really internalize it as, you know, perhaps the most powerful theorem in PDEs. A lot of people will disagree with me, but, you know, we're all entitled to our own opinions. Anyway, I'll see you in the next class. Bye.